All right, so let's continue to talk about Lewis structures here. Next week will be the last week, so I plan to have maybe next Thursday a review. And the test I made, the test is 25 multiple choice questions, and I'll have the study guide by Sunday. Okay? I'll have a study guide hopefully by Sunday. I've just been very busy with a lot of other stuff going on. And it's going to be on chapters 7, 8, and then 9 and 10 I joined together. I think the last time where we left off was resonance. Okay, so resonance structures are there. They're very stable. Let's just go over some more Lewis structures. Okay, some things that you may see on the exam on November 24th. So, all right. So test 4 is going to be November 24th, so that's the last day of class. You do not have to come that day, okay? So not next week, but the week after. It's the last day. And it's 25 multiple choice questions. All right, so that's all. And each one is worth 2 points, so that's worth 50 points. Quiz 4 is due November 24th, so that's when quiz 4 is due. So I'll have a study guide for this up by this weekend. Just bear with me, just as you may understand, some of you, there's just a lot of stuff going on. So I'll put the study guide hopefully this weekend. Meanwhile, you can look over our old lecture notes. And as we wrap up the class, if you want to turn in your lab notebook, okay, I'll put in the 100 points. All right, so lab notebook, I don't have a specific due date, but we only have next week and then the following Tuesday. So you can just drop it off in class or put it in my door. Okay, I'll put 100 points. If you did not take the labs, I'll put the points, or I'll just add that percentage to your lab reports or something else. I'll see what I'll do. So lab notebook is due. Okay, make sure all of you have your lab reports uploaded. Okay, got a lot of lab reports that I'm going to grade, and that's it. We're finished with the lab reports. Molecular models is the one that you guys should be working on your own. And the ones we did together as a group was solubility within a family. So if you want to do that, there is a student who wants to do this. I guess she learns better that way. So if you want to do this lab, you can talk to me or Larissa. So, but next week is your last week to do it. I guess you can do it today, but we just need some preparation. Anything else? I think that's it. Okay. There's that online thing, Clutch Prep. Okay, so check that out. I don't know who's doing it, who's not doing it. Okay, it's only meant to help, not to hurt. So do those drills. Okay, help you solidify and fortify the information when you take Chemistry 2. Alright, so the big thing is our test and our quiz. And, there's one more thing. I do have an extra credit set. I do not have to do it, but it's 40 Lewis structures. So you'll draw them, check your answers with my answers. Okay, write down, do the assignment, and I'll give you 25 points extra credit, and that goes towards the homework contribution of your grade. Towards your homework percentage, and I don't have a due date, but you just have next week. Okay, because again, Tuesday the 24th is the last day. I'll probably this Thursday or tomorrow I'll give you firm due dates. Okay. Again, it's 40 Lewis structures. Draw the structures, and it's an honor system also. Right, just gives you more practice.
Is there a problem set too? I mean, there's the test, like multiple choice.
No, I decided not to do a problem set. Okay, just 25 multiple choice. And I'll give you the study guide. It's basically from the old lecture notes or the lecture notes we've had so far. So that's definitely where you would go to study this. And we'll have a review next Thursday, which will be our final day. Anything else? Questions? All right, let's do a couple of Lewis structures here. So here's one that will be on the exam. It's called SF6. Okay, this is called sulfur hexafluoride. So the way you want to do this is take the atom, okay, sulfur. All right, how many valence electrons are in sulfur, or what is sulfur happy at? 6 is the right answer. Very good. Sulfur is happy at 6. Fluorine is happy at 7. Okay, but we've got 6 of those. Okay, so 7 times 6 is 42. So our goal is to get 42 plus 6. Our goal is to get 48 valence electrons around the SF6 molecule. So I'm going to make sulfur my center atom. Right? I'm going to make sulfur my center atom because you see I don't know which one of the 6 fluorines can be center. So that doesn't make sense to have fluorine as the center because which one of the 6? So let's choose sulfur as our center atom. And I'm going to draw this 1D, one dimension. So we will have 1F, 2F, 3F, 4F, 5F, and then 6F. Alright, so let's count the electrons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That looks like an expanded octet for the sulfur, by the way. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, count with me. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. So I got all my 48 valence electrons accounted for. Okay, all 48 electrons are accounted. The next thing we want to do is look at our octet rule and formal charge. Okay, first thing is formal charge. So let's do the formal charge of the sulfur atom. Okay, ready? 1, 2, 3, 4, 5, 6. What is sulfur happy at? 6. What's 6 minus 6? 0. Okay, so the formal charge on that sulfur atom is going to be 0. Now let's do the octet rule for the sulfur. Okay, ready? 1, 2. Count everything individually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so it's 12, but that's okay. That's okay. Okay, because we can have what's called an expanded octet. So sulfur, through whatever ways or means, can pick up those 12, can do the expanded form. Okay, can bond 6. 1, 2, 3, 4, 5, 6. Alright, so formal charge on that sulfur is 0. Let's pick on the fluorines here. I'll just do 1 fluorine. I'm not going to do all 6. Alright, so the formal charge on the fluorine atom. Alright, ready? Okay, we'll count with me. 1, 2, 3, 4, 5, 6, 7. I'll do it again. 1, 2, 3, 4, 5, 6, 7. What is fluorine happy at? 7. What's 7 minus 7? 0. So the formal charge on the fluorine is 0. Formal charge on all the fluorines is 0. So there's it's a 0 charge. There's a 0 charge. Octet rule for the fluorine. Okay, 1, 2, 3, 4, 5, 6, 7, 8. You count everything individually. 7, 8. So the octet rule for the fluorine is satisfied. So this is the best structure for SF6, sulfur hexafluoride. All right. Another thing we want to look into is hybridization, sort of the mixing of the orbitals. How do we get 6? Okay. By the way, do you guys agree, Elena and everyone, Hazel, do you guys agree this is 6 bonds and 0 lone pairs? Okay, 6 bonds, 0 lone pairs. 6 bonds, 6 single bonds and 0 lone pairs. So 6 bonds and 0 lone pairs, how do I get to 6? Okay, I'm going to take 1 from S. Okay, I'm going to take, well, P only has 3 slots. 3 from P. 3 plus 1 is 4. I need 6. Now I'm starting to go to the D orbitals. Okay. So this would be an sp3d2 hybridized sulfur. Right? 2 plus 3 is 5. 5 plus 1 is 6. 6 bonds, 0 lone pairs. Okay, 6 bonds, 0 lone pairs. This is where I want you to go to either table 10.1 or table 10.2. Okay, so you can have these on your exam or use whatever internet source you want on your exam. If I remember, I'll put these up also. So you want to use table 10.1 because the central atom has 0 lone pairs. Okay, 0 lone pairs. So 2 bonds, 3 bonds, 4 bonds, 5 bonds, 6 bonds. 6 bonds, 0 lone pairs. The geometry of which is going to be octahedral. In fact, they even gave you the example octahedral here for SF6. Octahedral. So the molecular geometry is octahedral. You see, all of these molecules have 3 dimensions. They're three-dimensional entities. So the molecular geometry here is octahedral. So let's build this. Okay, so I got something with 6. SF6. Okay, so we didn't have the virus. I'd have you guys come up here and do this with me. there's, you see here 1, 2, 3, 4. That's one tetrahedron, if you want to call it that. 1, 2, 3, 4. That's a second tetrahedron, or whatever you want to call it. So 4 on the top, 4 at the bottom, 8. So that's where you get the octahedral geometry. Okay, how will we draw this in 3 dimensions? Okay, so remember there's many ways, okay, because the molecule, undergoes all sorts of rotation. So let's draw it this way. All right, so all right. Realizing there's more than one way to draw this, so I'm going to try to draw this in 3 dimensions. So here's our center atom. So I have this on the plane, this bottom on the plane, this left one and right one, they're all on the plane of my chest. Again, this is one way to draw it. All right, I got 1 sulfur, so I got 1 fluorine up, 1 fluorine down, 1 fluorine to the left, 1 fluorine to the right, and I have a fluorine pointing towards there. So the fluorine pointing towards there, okay, we're going to use what's called it's called a wedge. Okay. Again, there's more than one way to draw this. One that's pointing towards me, okay, away from you guys and towards me, away from you guys, is, we'll call that a dash. Okay, we'll use the dash. We'll do the dash. So this bond here that's colored black is called wedge. This bond here that is going away from you guys, we'll call it a dash. Okay. So a dash bond and a wedge bond. Let's see if I can do this a little bit better. Definitely not Picasso here. So one thing, and I do not know if, again, many people are good seeing 3D. If you take the center of each circle, so I'm going to take the center of this atom, this atom, this atom, that, and that. If I take the center of all the atoms and sort of connect them, and this may be hard to see, but you should see a tetrahedron on the top and then a tetrahedron on the bottom. Okay, sort of looking down. Imagine you're on a helicopter, okay, looking down. Okay, on an airplane, you're looking down. Looking down, you're going to see it from here. Okay, this vantage point. So, tetrahedron, you're looking down like this. Anyways, a tetrahedron on top, tetrahedron on the bottom. Octahedral is the geometry. Again, you're looking down. All right, is this polar or non-polar? Okay, that's our next question. So you see this fluorine is an electronegative element, so it's pulling down. So it's going to be a delta negative pulling down, and then you have a delta negative pulling up. Okay, here we have this fluorine pulling in that direction, and I want to, hopefully I can convince you, or you can see that this fluorine here is pulling to counteract that. We have a fluorine here that's pulling in its own way. It's like an electronegative, like a vacuum cleaner, sucking power of electron density. And that's being counterbalanced by the fluorine here, pulling in an equal but opposite direction. So this molecule, SF6, is nonpolar. Nonpolar. It's a nonpolar molecule. So SF6, 48 valence electrons, nonpolar, sp3d2, octahedral is the molecular geometry. We get that from looking at table 10.1, or if it's lone pairs, table 10.2. Let's do a couple of more examples here. How about this molecule here, I3 minus? Okay, this is one of the more difficult ones, I3 minus. So I is happy at 7. Okay, but we don't have 1, but we have 3. So 7 times 3 is 21. Okay, that minus sign means that we gain an electron. So our goal is to get 22 valence electrons around I3 minus, that ion. All right, so we're going to make iodine our central atom. We'll make it bound to iodine here on the left, and we'll make it bound to the iodine here on the right. Okay, so 22 valence electrons. All right, count with me. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Where do you think the others will go? They don't like double bonds. It will go here. 17, 18, 19, 20, 21, 22. Why will there be no double bonds here? Okay, if you put a double bond, well, first of all, halogens will not take double bonds for the most part. Okay, there's always exceptions. You have a double bond with the iodine, it will mess up the formal charge. It will really mess up the formal charge and mess up the octet. It will mess up a whole bunch of things. Remember, minimize the octet and minimize formal charge, try to get an octet. Minimize the formal charge, try to get an octet. Minimize the formal charge, try to get an octet. So let's count these one more time here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. All right, let me tell you why I did this. Formal charge on this iodine, the center iodine. Okay, ready? I want you to count with me. 1, 2, 3, 4, 5, 6, 7, 8. What is iodine happy at? 7. What's 7 minus 8? -1. Okay, so the formal charge is -1. Well, that's what they tell you in the problem. Okay. See that? Hazel, get that? Okay, so let me go over that again. Minus formal charge, okay? So formal charge on this iodine, 1, 2, 3, 4, 5, 6, 7, 8. Iodine happy at 7. 7 minus 8 is minus 1. There's that minus 1. Okay. So that is accounted for, which is good. Okay, let's look at this iodine, which is the same as that one. Okay, formal charge. Ready? 1, 2, 3, 4, 5, 6, 7. Right? Once again, 1, 2, 3, 4, 5, 6, 7. What is iodine happy at? 7. What's 7 minus 7? So with a formal charge on this and that iodine is 0. Okay, let's do the octet rule. Okay, this center iodine in green. Okay, ready? Count everything for the octet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's okay. That's okay. Okay, we'll call this an expanded octet. Okay, there's a lot of wishy-washy. There's a lot of... The octet rule is not set in stone. If we can get an 8, great. If not, that's okay. The expanded octet on the center is fine. On the center atom is fine. All right, how about the octet rule for the outer iodines? Okay, ready? Count with me. Okay, octet rule, you're going to count everything individually. Okay, count everything individually. So 1, 2, 3, 4, 5, 6, 7, 8. So the octet rule is satisfied there. I got my 22 valence electrons. I got my negative formal charge. This is a great structure of I3 minus. Okay, this is the best structure. If you start putting double bonds and this and that, it'll get messy. All right, so how will we do this? How many bonds here? We got 2 bonds. And how many lone pairs? 1, 2, 3. So 2 bonds and 3 lone pairs. Okay, 2 bonds, 3 lone pairs. Two bonds, 3 lone pairs. So now we'll go to table 10.2. Okay, so make sure you bring this to the exam. All right, so 2 bonds. Number of lone pairs is 3. And the geometry, everyone see this? The geometry is linear. Okay, and they even gave you the example that I'm showing you, I3 minus. So somehow those 3 lone pairs distort the molecule to make it linear. Okay, I3 minus. Okay. So the molecular geometry is linear. Those lone pairs, they really mess up the structure of the molecule. They don't make it nice and pretty, especially with water. Okay. The molecular geometry here is linear. Okay. How will we get to 5? So we have 2 bonds, 3 lone pairs. 2 plus 3 is 5, so we'll take 1 from S. P only holds 3, so we'll take 3 from P. That gives us 4. And then what can we take from D? How many? We'll take 1 from D. So S, P3, D. Okay. 1 from the S plus 3 from the P is 4 plus 1 from the D is 5. So it's an sp3d hybridized iodine. Okay, let's see if I can draw this, or if we can build this. So I3 minus. why they call this a line, linear, but it's strange.
I was thinking you moved that one. Move that one to the. Yeah. Yeah. And then move the one that you had.
Well, you can see what happens to the lone pairs when they do. And where will the third one go? On the bottom. Okay, somehow this is a line. Okay, so lone pair here, lone pair there. Okay. Probably what you don't see the effects of that lone pair. There's actually 3 lone pairs, right? 1, 2. Wait, hold on. 1, 2, 3, 4, 5. Lone pair 1, 1. Oh, you know what? I know what I did wrong. Because there should be 3 lone pairs. So maybe I do this. I'm not seeing this, but anyways, you'll have to trust your textbook. It's a linear molecule. Okay, lone pairs, they sort of make this all into a straight line. Yes, okay, I got it. Here's I3, okay? So here's your I number 1, I number 2. Here's your center I with the 3 lone pairs. Here's lone pair 1, lone pair 2, and then lone pair 3. Okay, so iodine outer, it's a straight line. Okay, thank you. So I forgot this was an iodine. Yeah. That's an iodine, that's an iodine. So it's a straight line, linear molecule. So how will we draw this in 3 dimensions? Okay, so here's my center I in the red. Okay, here's my other I on the leftmost side. And then here's my other I in the rightmost side. Okay, so I think what I'll do is I'll have these 2 pairs of electrons. Okay, there's a pair of electrons that's coming out towards me. So I'll do it like this. Okay, that's coming out away from you guys. And then I have 2 pairs of electrons. One is coming this way. The other one's going that way. Okay, one's going this way, one's going that way. Okay, this one's going there, that one's going there. Okay, so I'll have one going this way. Again, there's more than one ways to draw this in 3-dimensional space. Okay, so this means it's coming towards you guys, if you can imagine it. And it's coming here. Okay, again, this is just one rendition. Okay, it's just one rendition. And this is where the lone pairs would be. Okay. So here we have a lone pair. Here we have a lone pair. And then here we have a lone pair. So what's really 3D is the lone pairs, okay, coming towards you and then sort of coming away from you. Okay. Now one coming away from you guys, and then one coming towards you guys at an angle, and the other one's coming at an angle towards you. Okay, this is called a wedge, and that's called a dash. Okay. Again, this is one way. There's more than one right answer if you want to draw this in 3 dimensions. All right, so all of my 3 lone pairs, those are my 3 lone pairs. All right, is this polar or non-polar? All right, so you see this iodine on the left, it's pulling. Okay, it's counterbalanced by the iodine on the right, which is pulling, equal and opposite. Right, now, a lot of people will get this wrong, but this is what is essentially happening. You see this electron that's at the bottom? Okay, this electron that's right towards me. Okay, that's pulling down. Okay, but you see this electron that's at an angle, it's pulling this way. And this one at an angle is pulling that away diagonally. Okay, if you add them up, the net of something going this way and the net something going that way, the net is, if you add this one here and that one there, if you add 1 and 2, if you add those 2 vectors, the net is going to be this way. Which actually counterbalances these bottom electrons. Okay, so adding gray number 1 with the gray number 2 vectors, dipoles is what it's called. Adding 1 and 2 will give me the net, 1 plus 2. So the answer to this question on whether this is polar or non-polar in terms of polarity, the answer is that this molecule is non-polar. Okay, a lot of people miss that, but it's non-polar. Okay, because you see the electrons at an angle here, at an angle there. When you add those up, they build on each other. And when they build on each other, the sum is going to be up, which cancels out this lone pair of electrons pulling down. So the net of this plus this cancels out that. The iodine on the left cancels out the iodine pull on the right. So this is a nonpolar molecule. Okay? So I3 minus sp3d hybridized iodine, nonpolar because of the sum of these 2 poles, balance out that one. The left and the right pole balance each other out. 2 bonds, 3 lone pairs. 2 bonds, 3 lone pairs, 22 valence electrons. The molecular geometry is linear. Molecular geometry is linear. Okay. That's kind of tricky, right? A little bit tricky. All right, let's do one more here, and then see where we are at. Let's do a molecule here called ICl3. Okay, this is called iodine trichloride. All right, iodine is happy at 7. Chlorine is happy at 7, but we have 3 of them, so 7 times 3 is 21. So our goal is to get 28 valence electrons around ICl3. Iodine trichloride is the name of this molecule. So let's make iodine our center atom because we don't know which one of the 3 chlorines will be center. So iodine, 1, 2, 3. Okay. All right, let's count our electrons here. Count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, let's put them back on the center atom because that will get the formal charge to fix, okay, to get it right. Okay, double bonds with halogens, unless very rare, but it's just not good because it messes up formal charge. All right, to prove why the 2 lone pairs should go back on the iodine center atom, let's calculate formal charge. All right, formal charge on this iodine, let's count. Count with me. 1, 2, 3, 4, 5, 6, 7. What's iodine happy at? 7. What's 7 minus 7? 0. Okay, so beautiful. Okay, you see, if you start doing anything else, you're not going to get the right formal charge. What about the octet rule? Okay, ready? Count everything individually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's okay. That's okay, and that's okay because iodine can have an expanded octet. As long as I get my formal charge to 0, I'm fine. You see there's 0 charge here, so there should be 0 charge on your structure. All right, let's do chlorine. I'm only going to do 1 chlorine. I'm not going to do all 3, so, just to save some time. All right, formal charge on this chlorine. Is yellow okay? No, yellow's not okay. Formal charge on this chlorine. Okay, count with me. 1, 2, 3, 4, 5, 6, 7. What is chlorine happy at? 7. What's 7 minus 7? 0. Okay, 0 charge. Same thing on that chlorine, same thing on that chlorine. I'm not going to do that again. Okay. Octet rule for this chlorine. Okay, count everything individually. So ready? 1, 2, 3, 4, 5, 6, 7, 8. Octet rule is satisfied. 0 charge here, 0 charge on the problem. This is good. Okay, this is the best. This is the best structure of ICl3. All right, check this out here. We have on ICl3, we have 1, 2, 3. We've got 3 bonds. And how many lone pairs? How many lone pairs? Okay, we've got 3 bonds and 2 lone pairs. 3 bonds and 2 lone pairs. So let's look at the situation where we have 3 bonds and 2 lone pairs. Okay, so 3 bonds, 2 lone pairs. The geometry is T-shaped. T-shaped. Okay, so the molecular geometry for this molecule is T-shaped. T-shaped. All right, how will we get 3 plus 2? How will we get to 5? Okay, what I'm talking about is hybridization. Okay, the mixing of orbitals. So how will we get to 5? All right, we'll take 1 from S. Okay, we can take 3 from P, and then we have nothing else left but D. So 3 plus 1 is 4. 4 plus 1 of the D's is going to be 5. Right, 1D plus 3 is 4. 4 plus 1 is 5. This is an sp3d hybridized iodine atom. Okay, hybridization basically is mixing the orbitals. How the orbitals come together is complicated, but they have to come together in order to get 5 bonds, 3 of which are single, 2 of which are lone pair for ICl3. Okay, let's see if we can draw this, make this ICl3. So IClCl, and then IClClCl, ICl3. Okay, T-shape. It does look like a T. Okay. How will we draw this in 3 dimensions? Okay, so here's a lone pair coming towards out you guys. Here's a lone pair coming towards me. Okay, so looks like the T is on the plane of my chest, plane of the piece of paper. So let's see if we can draw this. We have an I here. We have a Cl. We have a Cl. Cl. This one coming towards me, away from you. Let's have this go this way. Okay. And then, this one that's coming towards me, you see this? It's coming towards me, and then this one coming towards you guys. It's kind of at an angle. Like this one is coming here, that one's coming there. Again, this is kind of, I don't know. Everyone sees things differently in 3D, so this would be that one coming towards you guys. Just putting the lone pairs in some sort of lobe, some sort of orbital. All right, is this polar or non-polar? I may have not drawn this properly, but you see this Cl is going to pull this way. That Cl is going to pull that way, so they cancel. Okay, this Cl is going to pull down. Okay, what's the net of something back and then something forward? What's the net? You see the net of this one and that one. Again, if you add them up, it's going to be this way. Okay. It has to do with the addition of vectors, which you'll learn in physics class. But this pull at an angle, that pull at an angle, the net, this pull at an angle, that pull of an angle, at an angle, the net is here. Okay. So the net of 1 and 2, when you add them up, will offset this Cl going down. Okay, so what I want to convince you is that this is a nonpolar molecule. Okay, because that at an angle, let's see if I can do it better here. Okay, this coming towards me, that one coming towards you, add them up, it balances out this. Okay. The pull of this coming towards me, that coming towards you guys, add them up, it's going to be this. Okay, this pull cancels out that pull. This pull cancels out that pull. It's nonpolar. All right, ICl3 iodine trichloride. 3 bonds, 2 lone pairs. The molecular geometry is T-shaped. It's a nonpolar molecule. The poles of electronegativity cancel each other out. This lone pair at an angle, that lone pair at an angle, when we add them up, cancels out this bottom. The Cl pull on the left cancels out the Cl pull on the right. This is nonpolar. This is an sp3d hybridized central iodine atom. Now let's take a little brief detour. We'll do some more on Tuesday, next Tuesday, and then next Thursday we'll review. I just want to talk a little bit about sigma bonds and pi bonds. Okay, so let's keep this very simple. Okay, this is the Greek letter sigma. Okay, and obviously pi is the Greek for pi. Okay, a sigma bond is an overlap of 2 s orbitals. Okay, 2 of them. And an s orbital is a sphere. Okay? Remember what an s orbital looks like? Just jog your memory. An s orbital is a sphere. And that is also the same thing as a single bond. So single bond, sigma bond, they're actually synonymous. And then a pi bond is an overlap of an s orbital. Actually, never mind that. A pi bond is an overlap of p orbitals. Let's just put it that way. Okay? An overlap of p orbitals. Remember what a p orbital looks like? Okay, it's a dumbbell along x. It's a dumbbell along y. It's a dumbbell along the z-axis. Okay, that's the shape of a p orbital. Okay, an overlap of a p orbital is a pi bond, and that also signifies a double bond. Okay. So a double bond and a pi bond are kind of the same thing. And then finally, let me tell you about a triple bond. Okay, that is an overlap of 2 p orbitals. Okay, 2 orbitals that are p. Okay, remember, what is a p orbital? It's a dumbbell. Okay, remember what an s orbital is? It's a sphere. Okay. I don't know how to draw a sphere, but it's a sphere. And then a p orbital is best represented by a dumbbell with the 0 energy in the middle. That's called a node, but that's a dumbbell. All right, let me give you some examples. An example I'd like to give you to illustrate sigma bonds and pi bonds is formaldehyde. for everyone that's in biology class or pathology class or whatever, these anatomy classes, they definitely use formaldehyde, which is CH2O. All right, carbon will be our center atom. Carbon must have 4. Okay, no matter what. If there's anything you learn from this class, carbon and 4 go together like, bees and honey. Okay, so 1 hydrogen, 2 hydrogen, and we'll make a double bond here. So that is the correct structure of formaldehyde. I want to focus your attention here on this double bond. Okay, so I'm going to rotate this formaldehyde this way. I'm just going to do a 90-degree turn. All right, this single bond is also called a sigma. It's also called sigma. It's an overlap of an s orbital. So the s orbital is a sphere, so I'm going to have a sphere here representing the s orbital of the carbon, and then the s orbital of the hydrogen, and then here's an s orbital of this hydrogen. Okay, they are overlapping, okay, constructively overlapping. And there's good flow. Okay, remember, wave particles of electrons. So we have s orbital overlap, which is what a single bond is. I want you to recognize a single bond is just a sigma bond. Same thing here. Okay, we have nice overlap. Okay, with the s orbital, which is sort of highlighted in pencil. Okay, but remember, what is a double bond? Okay, a double bond is also an overlap of a p orbital. Okay, so I'll draw the p orbital. Maybe I'll draw it in gray. Okay, what does a p orbital look like? Okay, it looks like a dumbbell, so it can either be an x, y, or z. I think I will draw the p orbital in green. Okay. Okay, so one p orbital of the carbon is overlapping, and they overlap nicely. Okay. And here's a successful overlap of a p orbital. The p orbital from carbon is overlapping with the p orbital from oxygen, and it's a good overlap, successful overlap, constructive overlap, because these things are waves as well as particles, and this is what we'll call the pi bond here. Okay. And that's how formaldehyde forms. Okay, so one of the p orbitals gives you the pi bond, and then in pencil we have the s orbital overlap. Okay, so double bond is a overlap of one p orbital. Okay, let me give you another example, this time with a triple bond. And an example of something with a triple bond will be cyanic acid. Okay, cyanic acid. So triple bond, we're going to overlap not one p lobe, but 2 p lobes. Okay, triple bond is an overlap of 2 p lobes. The example I'd like to point out to you guys is cyanic acid. HCN. Okay, carbon loves 4, so I'll have the H with the carbon. How will I get to 4? In this case, it's going to be a triple bond. All right. This carbon here, last 10 minutes of class. This carbon here has two bonds. Okay, one is single, the other is triple. It has two bonds and 0 lone pairs. You see that? One of them is single, the second one is triple, 2 bonds, 0 lone pairs. Table 10.1, 2 bonds and 0 lone pairs. Table 10.1, because no lone pairs, 2 bonds and 0 lone pairs, linear. So this molecule is a straight line. It's a straight line. And the molecular geometry is linear. Okay, how will I get to 2? 2 plus 0 is 2. How will I get to 2 in terms of hybridization? Okay, I'm going to get 1 from S. That's 1. Where will I get the other one from? P. Okay, so this is an sp hybridized carbon. And then finally, carbon is not very electronegative. Hydrogen is very wimpy. Okay, hydrogen is a wimp. But this nitrogen has a little bit of pull, and then we also have a lone pair of electrons here. Okay, so remember, hydrogen is happy at 1, carbon is happy at 4, nitrogen is happy at 5. So we need 10 valence electrons. Here are my 10. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8, and then 9 and 10. Okay, they go on the nitrogen. All right, so nitrogen is going to do a lot of pull because of the lone pairs. This is a polar molecule. Okay. So cyanic acid is linear, 2 bonds, 0 lone pairs. It's a polar molecule, sp hybridized carbon. Okay. I want you guys to pay attention to this triple bond here. All right, so let's draw cyanic acid again. Let's draw cyanic acid again. Okay, the single bond here is an overlap of s orbitals. So an s orbital is mostly a sphere. Okay, we also have some overlap of s orbitals with the carbon and the nitrogen, so I'll just add that. So what's shown in pencil are the sigma bonds, which is sigma bond is an overlap of the s. Okay, so we have some nice overlap between the s orbitals. All right. Now we have the triple bond here. That's 2p. Okay, so I'll have 1p. I'll have 1p as we had in our previous example, like this. So 1p lobe of carbon will overlap with 1p lobe of the nitrogen. Nice overlap here. So that is an overlap of one of the p's, but this is a triple bond we're talking about. So we need one more p. We need one more p, and I'll do that in pink. Okay, and that one p is going to be perpendicular. Remember, these guys are perpendicular to each other. Okay. So the green and the pink are perpendicular to one another, and that is a triple bond. Okay, P lobe green and the P lobe in pink are going to overlap. Some nice overlap here. Okay. So in the green, I'm going to call it P lobe, P orbital 1. That's overlapping. P orbital overlap. And then in pink is the second P orbital overlap. And that is what a triple bond is. Okay, so in review, triple bond is 2 P lobe overlap and 1 S orbital overlap. Oops, overlap of two P orbitals. P is in the shape of a dumbbell, and 1 S orbital. Okay, that's a triple bond. A double bond is an overlap of 1 P orbital. So if you have a double bond, it's just one of the P's coming together. If you have a triple bond, it's 2 of the P's coming together. Each P is perpendicular. All right. There's just a couple of more things I want to talk about, just briefly points that I'm going to hit on. I'll do that Tuesday, and then Thursday we'll review for the exam. And then Tuesday you'll take your exam, and then you'll be done with the course. That is Tuesday, November 24th. Okay? So next week is our final week. And check your Canvas. Make sure you got everything uploaded that you want uploaded. And I'll see you next week. Have a good weekend. Yep. Any questions or comments, you can email me. I should have office hours on Friday for 2 hours or so. And I'll send you that Zoom link.